champions, welcome back to the Brahmastra 2.0 series, and in today's video we are going to discuss the most important questions from the chapter Haloalkanes and Haloarenes. So in this video all the important questions are covered, and if you do practice of these questions then you can get full marks in this chapter in your PU2 boards. Okay, so before starting let us understand the weightage of this chapter. So this chapter has a weightage of 9 marks, okay, and this 9 mark is distributed how? So this 9 marks, 2 marks will be for your MCQ questions, or I can say 1 marker question. It can be in the form of fill in the blanks or MCQ. After that you will be having 1 2 marker question and 1 5 marker question. Okay, so 5 6 7 8 and 9. Clear? Now let's move to the first question. So I have taken some very interesting MCQs for all of you. I have included HOTS question. Okay, so these are high order thinking questions, so definitely you have to think, if you need to have some deeper understanding of the concepts to solve this question. So let's start with that. Okay, so let us see the first question here. Statement number 1 is enantiomers are non-superimposable mirror images on each other. So this is the very basic definition of enantiomers, that is they are non-superimposable mirror images on each other. Now the next one is a racemic mixture shows zero optical rotation. Now here it is important to understand what is a racemic mixture. So a racemic mixture contains equal proportion of both the enantiomers, plus and minus, or D or L. Now if D rotates the plane polarized light in clockwise direction, L will rotate the clockwise in the anti-clockwise direction, right? So that is why both the isomers are present in equal amount, okay, and that it shows optical rotation. So that is why this statement is also correct. So option number A is the correct answer. Next we have 1,2-dichloroethane is an example of. So we have here 1,2-dichloroethane is an example of. So here you have in the vicinity, means very close to each other, we have both the chlorine, so it is vicinal dihalides, okay, and it is also called as alkyline dihalides. Okay, so here both A and C are the correct answer. Next, moving to question number 3, 4 haloalkanes compounds are represented by letter M, N, O and P, have boiling points 24.2, 38, 33.56 and 101.6 degrees Celsius respectively. Among the 4 compounds, N is mostly like to be. Now you see these are the 4 compounds given, okay. So you see the order is like this: M is 24.2, N is 35, then okay, I'll write like this: O is 3.56 and P is the highest one, right? So if the order comes like this, first highest is definitely P, which is 101.6. okay, after that we have so okay, let me just write down here, I'm like to get a clear vision of the boiling points. So what is the value of M here? 24.2 degrees Celsius. N value is 38.38 degrees Celsius. O value is 3.56. Then P value is 101.6. Okay. Now if you see here the values, P is around P is 101.6. okay. Then Q highest value will be N. After that it is N. Okay, after that it is M, and lastly we will have O, right? This is the order of boiling points. Now we know that if the mass boiling point is directly proportional to mass, right, means if the mass will increase then the boiling point will also increase, right? Now you have to match these 4 compounds to these 4 compounds and we can easily find which is N here. Okay, so now see which one will have the highest boiling point. You can see in the compound D we have number of carbon also more, and we have iodine also. The entire mass of this compound is more. So P is what? C3H7I. This is definitely P. Now if you see N, which is the second largest here, so you can see here I have 2 carbons and bromine, here I have 1 carbon and bromine, so its mass will be this one. So N will be C2H5Br. Okay, now coming to M and O. Now here you can see this mass will be more because you have one carbon and one bromine. So this one will be CH3Br, okay, and this one is CH3Cl. Okay, so now if you see here N, the C2H5Br, that is having more the value of N more suitable is C2H5Br. So that is why option number C is the correct answer. Next we have question number 4. The homologous series of alkyl halides are represented by the general formula. So we have the general formula CN for alkanes, it is 2n plus 2. Okay, now one of the hydrogen is replaced with X. So what will happen? The number of hydrogen is CnH2n plus 1 and there is a X group. So that is option number A here. Next we have the toluene reacts with a halogen in the presence of iron, giving ortho and para halo compounds. The reaction is, okay, so if you have toluene, okay, see the reaction here, toluene reacts with halogen in presence of iron chloride. Okay, so it reacts with halogen in presence of iron chloride. For giving ortho and para halo compounds, the reaction is. Now always remember that this compound benzene can always show electrophilic substitution reaction. Okay, electrophilic substitution reaction. The reason being, see, in this benzene ring there are lone pairs of electrons, right? And these lone pairs or these pi electrons are not tightly bound to the molecule or to the system. So they are these electrons are can be easily donated, or they this molecule behave as a good source of nucleophile. So it always attracts the electrophiles. Okay, so here that is why reaction is electrophilic substitution, which is option number B here. Next, which reagent will you use for the following reaction? So here what has happened, you have replaced, or there is chlorination, right? But chlorination is taking place in different carbons. You can have here also and here also. So that will happen if this reaction is possible in case of free radical mechanism, and free radical mechanism happens when you have chlorine with UV light. Okay. Next, we'll see question number 7. Arrange the following compounds in the increasing order of their boiling point. So for boiling point, you have to remember two things. Boiling point is directly proportional to mass, okay, and boiling point is inversely proportional to branching. Okay, so now if I see the first compound number B is a straight chain, so its boiling point will be the highest, so I can have only one option with that. So option number A is the, oh sorry, one second, yeah, I have only one option where B is the highest one, so that is why option number C has to be correct. Now after that, you see here there is 2 branches and here also we have 2 branches, right? But this is a primary and this is a tertiary, and here you can see the branching is more as compared to this one. So after B there will be A and lastly there will be C. Next we have the position of Br in the compound. This one can be classified as, so if you see the position of Br, so we have CH3 CH double bond CH C Br, yeah, then I have 2 CH3 groups. Okay, now if you see this compound, this is the carbon next to the, means the carbon containing the bromine group is next to the carbon having double bond, right? So it is an allylic group, that is why option number A here. Next, chlorobenzene is formed by the reaction of chlorine with benzene in the presence of AlCl3. Which of the following species attacks the benzene ring in this reaction? So chlorination happens when you have Cl+, that is option number B here. Okay. Next, what is A in the following reaction? So if you see here, this is very important question and a very, very important example also. Up to, if I say one of the most, you can see where you have to like do maximum mistake, but if you have understood this concept, then you will not do this mistake. Now see, what is the concept here? This is just the addition of, HCl right? So now what will happen when you add HCl? Okay, when you add HCl, what exactly happens? The bond will break and we will get a carbocation here. Normal Markovnikov's rule followed and Cl will be added here. Majority of the students will go and answer this option number C. Okay, but let me tell you here the twist. So what happens is, just imagine that you have formed this carbocation. Okay, so this is CH, right? So this bond shifts here and you have this carbocation like this. We have this one, that is CH2, CH plus and CH3. Okay, now this carbocation is formed here. Now this is a secondary carbocation. Now just imagine if the carbon, if the hydrogen from here, okay, I'll show the hydrogen with bond. So if the hydrogen from here shifts here, then what I will get? If the hydrogen shifts here, then you will get something like this. CH plus, CH2, H3. Okay. Now you see what is the speciality of this carbocation. This is also secondary carbocation, but apart from secondary carbocation, this carbocation is resonance stabilized. Okay, so if it is resonance stabilized, then it will be more stable, so chlorine will attack here and the final product will be this one, that is option number D here. Okay, now let's move to the 2-marker question. So in 2-marker section, generally you will be asked with the name reactions in this chapter. Okay, and there are certain name reactions you will have to write. So what is the basic format of writing a name reaction in the answer? So first you need to write the statement and then you have to give an example. Whether it is asked or not in the question, you always need to write an example for the name reaction. Okay, so let's see Schwartz reaction with an example. So alkyl fluorides, you know, Schwartz reaction is for the preparation of alkyl fluorides. So when you take alkyl chloride or bromide in presence of, so when you take alkyl chloride or bromide in the presence of metallic fluorides like AgF, Hg2F2, COF2 or SbF3, then alkyl fluorides are formed and this reaction is called as Schwartz reaction. Okay. Next we have Finkelstein reaction with example, the same thing when alkyl iodides, okay, are prepared by the reaction of alkyl chlorides or bromides with NaI in dry acetone, that is called as Finkelstein reaction, and here also you need to write the example definitely. So like CH3Cl, and if you take NaI with dry acetone, okay, so that will give me CH3I, right? Okay, next we have how do you prepare alkyl halides from alcohols? How do you prepare alkyl halides from alcohols? So there are different ways of preparing alkyl halides from alcohols. Okay, the best way is the method, or the best method used is by treating alkyl alcohols with SOCl2. Okay, that is because in SOCl2 the preferred or the byproducts are gaseous products, so easily pure haloalkane can be obtained. Okay, so now let's see the formula of the compound C5H10. Okay, so you can see the general formula of this one is CnH2n, right? This is either for alkenes. Okay, this general formula is either for alkenes or for cyclic compounds. Okay, so alkenes, if I do, I will never get the same mono-halo derivative. For example, if I have this particular compound, okay, I'll just make one random compound. Then definitely here if you put chlorine, you will get a different compound, and here if you add chlorine, you will get a different compound. But we need to get monochloro derivative, means all the groups should be same. So the other option that is there with me is the cyclic compound. So if I draw a structure like this, okay, 5, and you can see this is the formula is C5H10. So here all the hydrogens can be replaced, like any hydrogen you replaced with chlorine, you will get one chloro, or you will get chlorocyclopentane. Okay, so the product will always be the same, so that is why this is the answer. Okay, Next, we have question number 5. Give the preparation of aryl halides by Sandmeyer reaction. Okay, so what is for Sandmeyer reaction? In Sandmeyer reaction, first of all, aniline is taken. Okay, aniline is taken and it is reacted with nitrous acid to give benzene disonium chloride. Okay, now this benzene disonium chloride can react with CuCl or CuBr to give you aryl chloride or aryl bromide, and this reaction is called as Sandmeyer reaction. Okay, so if I have this one particular, that is you have first aniline, okay, and then you treat it with HNO2 nitrous acid, then you will get here N2 plus and Cl minus, okay, and after that if you treat it with CuCl, okay, then you have this particular compound, that is chlorobenzene. Okay, that is the reaction. Next, we have in haloarenes, the para isomers have high melting point as compared to the ortho and meta isomers. Why? So if you see, the para isomers have a symmetrical structure, right? So they can fit into the lattice better. So that is why they have higher melting points. So you can see here how to write this answer. Due to the symmetrical arrangement, para isomers can fit more tightly into the lattice. But ortho and meta isomers have non-symmetrical arrangement and form unoccupied space. So when you have meta, there is a lot of space between them. Okay, so therefore the para isomers have higher melting point as compared to ortho and meta isomers. Okay. Next, arrange in the increasing order of boiling point. So this is again, we have discussed the concept while discussing MCQs. So boiling point is directly proportional to mass, okay, and it is inversely proportional to branching. Okay, so these two things you should remember for boiling point. Now let us see the structure here. Bromomethane is CH3Br, okay, then you have bromoform is CHBr3, okay, then we have chloromethane, that is CH3Cl, and we have dibromomethane, that is CH2Br2. Okay, so this is the structure that we have. Now what we can do here is, so if you see the order, okay, order of the compounds, so if I see, the lowest one will be CH3Cl. Okay, the lowest one will be CH3Cl, then we will have CH3Br, okay, and then we have CH2Br2, okay, and then we have CHBr3. Okay, so this is the order. You can see as the bromine increases, the mass will increase. So that is the order of the boiling point. Next, we have 1-chloropropane, isopropyl chloride, and 1-chlorobutane. Okay, so you can see here isopropyl chloride and 1-chloropropane and 1-chlorobutane. So butane number of carbons is more, so its mass will be more. So definitely 1-chlorobutane will be the one with highest boiling point because of its mass. Why mass is more? Because we have more number of carbons there, right? Next, if you see isopropyl, this is a branch chain, this is a straight chain. So isopropyl will be the least one. Okay, so I'm just writing like this. Isopropyl will be the least one, and then I will have 1-chloropropane. Clear? So this will be the order of the boiling point. Next, write the steps involved in the SN1 mechanism for the conversion of tert butyl chloride to tert butyl alcohols. Okay, so SN1 mechanism, as we know, involved two steps. Okay, in the first step, what happens? So I'll just give you an example. So first, let's understand. So suppose this is our tertiary halides. Okay, now in the step 1, what happens? This X goes out and we get a carbocation formed here. Okay, this is a carbocation formed here. This is step 1. Now in this carbocation, what happens? The nucleophile is there, and this nucleophile can attack here, and we will get here Nu. Okay, so that is how the reaction can take place. Now I'll give you one example here. So you have to take this particular example of tert butyl chloride to tert butyl alcohol. Okay, no other example, because in question they have asked for that. So how can you write? See, this is tert butyl. I have taken bromide here, means the one which is given in the example in the book. So you should take here chlorine here. Okay, so in the step 1, remember what you have to write here. So you have to also mention the steps. So step 1 is what? Formation of carbocation. Okay, formation of carbocation. Now what is step 2? Step 2 is the attack of nucleophile, right? Now if you see here, in step 1 this bromine will go out, so we will get a carbocation formed here, and see we have to draw a reversible step here. Then after that the nucleophile will attack on this one, and you will have this particular thing, that is tert butyl alcohol. 2 steps, 2 marks. Next question, write the steps involved in the SN2 mechanism for the conversion of chloromethane to methanol. In SN2 what happens, it is a one step reaction, okay? So if in SN2 what happens, when you have this Rx, okay, Rx is there and this nucleophile comes, right? So this nucleophile attacks the R from the opposite side, and you will get nucleophile, then you will get R, and then you will get X. Now after that what happens, the Rx bond will break and this nucleophile and R bond will form here, okay? So now let's see the reaction. So here we have OH minus will attack from the back side, okay? Now if it is attacking from the back side, there will be a condition like this. This is called as transition state, okay? We will get a transition state here. Okay, now once this is formed, the chlorine will go out, okay, and this particular thing will remain plus Cl minus, okay, clear? Now haloalkanes react with KCN to form alkyl cyanides and with AgCN to form isocyanides. Explain. So this is very important question. So if you have understood, if you have seen the reactions table, the nucleophiles, okay, so you can see KCN will give you alkyl cyanides, but if you take AgCN you will get isocyanides. What is the difference here? So the difference is between the bonds in KCN and AgCN. KCN is a ionic compound, whereas AgCN is a covalent compound. So what happens, you can see here, KCN is ionic, so both C and N can donate the electrons, but C only donates because CC bond is more stable, okay? So means more stable with, see, you have this Rx, okay? Now you have KCN, okay? In that we got CN minus, okay? Now in this CN and both can donate electrons, but C, the R here, this R group is a C, right? So the CC bond here with the R is more stable. So that is why C forms bond and we get RCN. Now AgCN is a covalent in nature and N is free to donate the electron pair forming isocyanide. So when you have AgCN, right, so there is a covalent bond between this one. Okay, now when this bond is covalent, this carbon is not having any electron to donate. Okay, it is not having electron to donate, so it is not free. But nitrogen has the lone pair which can donate the electrons and can form bonds with the carbon. So here we get RNC. Okay. Next is electrophilic substitution reactions occur slowly in haloarenes compared to benzenes. Give reason. So now you see, if you have this we have this benzene ring, okay, and we have this haloarene, and you have this electrophile. Now the question is saying that this electrophile will react faster with benzene than with haloarenes. What is the reason for that? Now see, for reaction with electrophile, okay, the ring must be a nucleophile. Okay, electrophile can react better with nucleophile, so the ring must be nucleophilic or electron rich. Now this X group is what? It is a minus I group. It's a strong minus I effect or strong electron withdrawing effect. So it withdraws the electron from the ring. So this X group makes the ring electron deficient. Okay, now here there is, means if I compare the nucleophilicity of benzene here and here, the nucleophilicity of benzene here is maximum, but here it is least comparing to these two. So that is why benzenes will react faster. Okay, so how can you note down that? Due to the minus I effect of halogen atom, haloarenes have some tendency to withdraw the electrons from the benzene ring. Okay, it has the tendency to withdraw the electrons from the benzene ring. As a result, the ring get deactivated as compared to benzene, and hence electrophilic substitution reaction occurs slowly. Okay, Next, we'll see question number 12. Aryl halides are less reactive towards nucleophilic substitution. Give reason. So this can be a potential 3-marker question. There are 3 points in the exam in the book, so you need to write all the 3 points if it is asked in a 3-marker question. So how it will be asked? So generally your 5-marker questions will be in the form of 3 plus 2, right? So there this can be asked as a 3-marker question. So let us first understand all the 3 points. See, the first important reason is when you have this halogen, okay, it has lone pair. So this lone pair of electrons undergo resonance. So there is a bond, or there is a partial bond formed here. Okay, sorry. So now when this partial, there is always a partial bond formed between X and the ring. Now due to this partial bond, what will happen? The nucleophile, okay, nucleophile cannot attack, means cannot come and just remove X from here, because it is having partial bond with this particular carbon. Okay, so that is the first reason. The second reason is the hybridization of this carbon. This carbon is sp2 hybridized. Okay, now if it is sp2 hybridized and there is X, okay, the bond between this sp2 carbon and X is very weak, sorry, very strong. Okay, so because of this hybridization, this bond is very strong as compared to Rx, where this R is sp3. Okay, so this bond is weak compared to this bond because it is sp2 carbon. So that is why removing one X, because this bond is very strong, a nucleophile cannot just come and remove this X. Okay, that's the second reason. Third reason is somehow if the X goes also, you will get a carbocation here. A phenyl cation is formed which is highly unstable. Okay, so 3 reasons. First is the partial double bond character, second is the hybridization of carbon, and third one is your phenyl cation instability. Okay, so how can I write that? So I have mentioned here 2 reasons. Resonance effect, first one. So due to resonance between C and X, the bond has a partial double bond character, and hence it is difficult to substitute. Second one, due to the sp2 nature of the carbon in CX bond, it has more S character and hence holds the bond strongly. Okay, so these are the 2 reasons. Next, explain Fittig's reaction, Wood's Fittig reaction, and Fittig reaction. So I will just tell you how to write one of them. Other 2 you can write by your own. So I'll tell you what exactly these 3 reactions are. Okay, so first understand like this: Wood's reaction. Okay, first you have to understand Wood's reaction. In Wood's reaction, what we do, we take Rx, okay, and you take sodium in dry ether, okay, and that gives you RR. Okay, that's the first thing. Next we have Fittig reaction. Okay, in Fittig reaction you have 2 benzene ring, okay, and you have Na, and if you use dry ether you will get 2 benzene ring are connected. Okay, now if you combine these 2, okay, that is your Wood's Fittig reaction. Okay, in Wood's Fittig reaction you take one Rx and you take this ARX. Okay, so that will give me R benzene ring. Okay, this is formed. Okay, so that is how you have to understand the difference between 3 of them, and I'll show you how to write one. So I am just giving the example of Fittig reaction here. Okay, so aryl halides when treated with sodium in dry ether give compounds where 2 aryl groups are joined together. It is called as Fittig reaction. Now if you want to write for Wood's reaction, what will you write? Alkyl halides when treated with sodium dry ether in a given compound where 2 alkyl groups are joined together. Okay, that is called as Wood's reaction. So here you can write the example also. This compound is called as diphenyl. Okay, next, what is Grignard reagent, and write its general formula. So the organomagnesium halides RMgX are called as Grignard reagent, and what is its general formula? It is RMgX. Okay, next, what are freons, and name the poisonous gas involved when Cl2 is oxidized by air. Okay, so what are freons? Freons are chlorofluorocarbons. Okay, the chlorofluorocarbon compounds of methane and ethane are collectively called as freons. Okay, and what is the poisonous gas is evolved when Cl2 is oxidized by air? Okay, so that is your COCl2. So sorry, not Cl2, it is chloroform. Okay, so when chloroform is oxidized by air, you get COCl2, or that gas is called as phosgene. Okay, next, chloroform is stored in the dark colored bottles. Why? So the reason is just what we discussed. Chloroform, when it is exposed to oxygen, it forms a toxic gas called as phosgen. Okay, so chloroform is slowly oxidized by air in the presence of light to a poisonous gas called COCl2, also known as phosgen. So CHCl3 plus O2 gives COCl2 plus 2HCl. Okay. Next we have complete. So now we will move to the 5-marker questions. Okay, so the 5-marker question, the first one is complete the following equation. Now if you see the first one, addition of HBr. Okay, addition of HBr, you know it follows Markovnikov's rule, right? Now those who don't know what is Markovnikov's rule, let me tell you. Whenever we have a addition reaction, okay, I'll give an example and I'll explain. So let's understand what is Markovnikov's rule. So suppose you have like this, okay, you are adding HBr, okay. Now in the addition of this HX, compound like the negative part, here which is the negative part, H plus and Br minus, right? So the negative part will go to the carbon with less number of hydrogen. So you have to compare this double bond, okay. Here you can see 1 hydrogen, here I can see 2 hydrogen. So the negative part will go to the carbon having less number of hydrogen. So what will be the product formed here? I'll have CH3, CH, Br, CH2 and H. Clear this one? So that is the product here. Now I think this is also 1, 2, 3. Yeah, this is also propene itself, right? So the product will be here. I can write the product directly here, that is CH3, CHBr, CH3. Okay. Now next one is, you have to write the reactant here, sodium diether. Now from sodium diether we have just understood that this is Wood's reaction, right? In Wood's reaction what happens? You need to have Rx and it will double, right? So here if you see there are total 4 carbons, right? So the reactant must be a 2 carbon compound. So you need to have C2H5Br. Okay, and when that will react, you will get C2H5, C2H5. So it will from 2 carbon it will become 4 carbon. Okay. Next question is NaOH 623 at 300 atm and H plus. So this is, you know, nucleophilic substitution reactions in benzene in haloarenes is very, very difficult. But at a very high temperature and pressure, we can do it, and this OH will replace this chlorine and you will have a compound like this. Okay. Next question is explain Saidzev rule with an example. So let's understand what is this Saidzev rule with an example. So I'll erase this one. So first of all, where is this Saidzev rule used? So Saidzev rule is used to find, so I'll explain here, okay, then we'll write the answer. Okay, let's understand here. What is Saidzev rule? Saidzev rule is used to find the most stable alkene after elimination reaction. Okay, most stable reaction, most stable alkene which is formed after the elimination reaction. Now let us take an example. Suppose I have this one CH3, okay, CH, CHBr, and I have CH2. Okay. Now see, there is a possibility of elimination of bromine, that you know alpha hydrogens are removed, right? So this is for example alpha carbon and this is the alpha hydrogen. So H and Br is there, so H and Br will be removed here. So you will get a compound like this, CH3, CH2, CH double bond CH2. This is one alkene formed. Now there is a possibility that this HBr can also be removed, right? So that will give me CH3, CH double bond CH, CH2. Okay. Now here you see this alkene group. Okay. Now this alkene group has how many carbons around it? It has 2 hydrogens, it has one, this side it has 2 hydrogen, this side it has 1 hydrogen, and you can see that there is 1 carbon in this, around this double bond, okay. And if you see this particular group, Okay, here I have 2 hydrogens and 2 carbon. So the Saytzeff rule says that this one will be the more stable product. Okay, so Saytzeff rule says that this one will be the more stable product. The reason being that it is more more covered with the alkene groups, okay, alkyl groups. So what is the rule now? Saytzeff rule. So Saytzeff rule, we can just write down what is Saytzeff rule. I'll erase all this. See, Saytzeff rule says that in case of elimination reaction, okay, the most stable alkene is formed. Okay, now how to define this most stable alkene? The alkene with more R groups is more stable. Okay, an example, just now I have written one example, you can write down that example. Okay, next write any 3 differences between SN1 and SN2. I'll show you some differences, we'll discuss about that. Identify A and B in the given reaction. Okay, this is very simple. So this one is diazotization. So what is A here? A will give you N2 plus and Cl minus. Okay, next what is B here? Once this is from benzene diazonium chloride, then what reagent can be added to convert it into bromobenzene? So you can use CuBr. Clear? Okay, next is I think it is visible. I'll just zoom it. Okay, the slightly blurry picture is there. Okay, so SN1 is it follows first order, SN2 is it follows second order. Okay, next SN1 involves 2 steps, SN2 involves 1 step. It involves the formation of carbocation. There is a formation of transition state. These 3 points are very, very important. Next, it's monomolecular and the back attack as well as the front attack can take place. It is retention in configuration, and here it is a bimolecular and only back attack can take place, and it is inversion in configuration. Order here it is 3 degree, 2 degree, 1 degree. Here it is 1 degree, 2 degree and 3 degree. Next, rate is equal to K into Rx, where you have the substituent only, means the substrate only, and here you have Rx and nucleophile both, so that is it is a second order reaction. Okay, I have read the points. If it is not visible, just you can zoom it and you can check it. Okay, next question, write the mechanism involved in the conversion of 2-bromo 2-methyl propane to 2-methyl propane to OL. Okay, so this is basically asking for your SN1 mechanism. We have already discussed, so I'll tell you how to write here. So first step, so you can say this is 3 plus 2 question, okay, 3 mark plus 2 marks, okay. So first thing you have to write is, write the reaction here. The question is asking for 2-bromo 2-methyl propane, right? So I have 2-bromo 2-methyl propane. So with OH minus, it will give me CH3, CH3, CH3OH, right? Now what is the step 1 involved here? Step 1 is formation of carbocation. Okay, I have already explained that in this 2 marker section. So here what will happen? You have this CH3 whole 3 Br. Okay, then with step 1 what will happen? It will give me CH3 whole 3 C plus. Okay, then what is step 2 here? Step 2 is attack of nucleophile. Okay, now here we have CH3 whole 3 C plus, and we have OH minus. Now this one attacks on this one, and we will get a compound like this. Okay, so this is the step 2. So this one reaction and 2 steps will give you 3 marks. Next question is, what are enantiomers, and name one physical property which differs in enantiomers. So this is again 2 markers. How will you define enantiomers? So see, enantiomers are non-superimposable mirror images on each other. Okay, enantiomers are non-superimposable mirror images of each other. Okay. Now name one physical properties which differs in enantiomers. Name one physical property which differs in enantiomers. So the physical property which differs in enantiomers means, so enantiomers have all the physical properties same, okay, their boiling point, melting point, density is same, but the only property which differs is the direction of rotation of plane polarized light. The direction of rotation of plane polarized light. Okay, so if one enantiomer is rotated in clockwise direction, the other one will rotate it in anti-clockwise direction. Okay, next question, write the equations for the step involved in the SN1 mechanism of 2-bromo-2-methyl propane. So already I have discussed this question. Okay, name the product formed for the reaction of isopropyl iodide on alcoholic KOH. What is the condition to be satisfied for a compound to be chiral? What is racemic mixture? So this question carries 2 marks. Okay, so you have to just write down 2 steps. This question carries 2 marks and this question carries 1 mark. Okay, so this one I have already discussed, 2-methyl, so similar to that only you have to write. Next, coming to this one. Yeah, so what is this? Name the product formed when we have isopropyl is reacting with alcoholic KOH. So if you have this isopropyl chloride and it is reacting with alcoholic KOH, so there will be elimination here. Okay, so you will get a double bond, this one. Okay, so you have to name the product, so it is propene. Okay, that's the first part. Next, what is the condition to be satisfied for a compound to be chiral? The condition is a carbon should have 4 different groups. Okay, carbon should have 4 different groups to be chiral. Okay. Next we have C. What is racemic mixture? So the racemic mixture consists of plus and minus. Okay, racemic mixture consists of plus and minus. Remember, both the enantiomers in equal proportions. Okay, racemic mixture consists of both the enantiomers in equal proportions, and that can lead. So equimolar mixture of dextrorotatory and levorotatory isomers is called as racemic mixture. Clear? Next question, primary alkyl halide C4H9Br reacted with alcoholic KOH to give compound B. Okay, so let us write down the first reaction, C4H9Br. Okay, primary alkyl halide C4H9Br, that is A. Okay, reacted with alcoholic KOH, okay, to give compound B. Okay, now compound B is reacting with HBr to give you C. Okay, compound B reacts with HBr to give C, which is an isomer of A. Okay, now when A is reacted with sodium metal, it gives you compound D. When A reacts with sodium metal, it gives me compound D. Okay, C8H18, which is different from the compound when N-butyl bromide is reacted with, okay, the formula of this one is C8H18. Okay, now this is second part is very interesting, which is different from the compound formed when N-butyl bromide is reacted with sodium. Now see, if there is, first of all, for the C4H9Br, what are the structures I can have? You can have one chain of all the 4 carbons, and you can have one structure like this. Okay, now the question is saying that primary alkyl halide, so you cannot add bromine here. Okay, it has to be a primary group, so this is the another structure possible. Now here it clarifies in the third part that D is not that product which will be when you have N-butyl bromide. If it is reacting, which product we will get? It is not that D. Means the D is not that product which we will get if N-butyl bromide reacts with sodium. So that clearly indicates that this is not the answer. This has to be the answer. Okay, so give the structural formula A and write the equations for all the reactions. So I can write down this one. that is this one I can write. Okay, now here there is Br and here there is H, so alcoholic KOH we have this one. Okay, now with HBr what will happen? Bromine will be added, so we have this one. Okay, next when this one is reacting with sodium diether, you will get a compound like this. This is 4 carbon and we have this one. Okay, so here you can see the different products that I'll get. So I'll write down the name of all them. So first of all, B will be what? B will be 2-methyl propene. Okay, I'm just done the structure. You have to write H also. Okay, 2-methyl propene. Next, what is C here? It is 2-bromo 2-methyl propane. 2-bromo 2-methyl propane. Okay, next D is what? D is when you reacting this one. So 1, 2, 3, 4, 5. 2 and 5. So 2,5-dimethyl hexane. 2,5-dimethyl hexane. Okay, so these are the products that we can have. So students, now let me tell you that if you are studying this chapter, there are some important concepts that you should never miss or you should not miss at all. Okay, so the first one is the definitions like retention, inversion, stereocenter, enantiomers, racemic mixture. Then all the name reactions you should prepare: Schwartz reaction, Finkelstein, Dow's process, Friedel-Crafts, alkylation and acylation, then Woods reaction, Fittig reaction, Woods-Fittig reaction, and Sandmeyer reaction. Then we have mechanism, SN1 and SN2 reactions. Okay, so prepare all these topics, and with this I think this session is over and I have discussed all the important questions. Make sure that you prepare these questions thoroughly. Okay, thank you so much for watching and all the best for the exams.